Thank you and welcome. Thanks for coming to talk. And I'm really glad to be here and honored to be here with all the experts in this area. I started working on the BANT at IEEE about 5 years ago. We started a study group around 2005, and I'll talk about a little bit about the process of standardization, but we started with collecting what we called an application matrix. And we asked all the organizations that were interested in body area networks to come and bring their applications, and we developed a giant document over 500 pages called BANT application that described about 140 different scenarios. And what came out of that was that we needed a system for providing links, communication links in and around the human body, like Marconi did for air, except instead of air, we had to deal with the human body, which is much different, to our surprise, than the air as a transmission medium. And we very quickly arrived at the sort of topology of the network of considering a hub and a node. Hub would be one or two, maybe one, optionally two things on your body that would collect all the information from all the different sensors. And we started talking about how many sensors there might be around the body, and at first it was one or two, then it was 10 or 20, and then it was 40. Then somebody said, in 1970, the average American car had one microprocessor in it. In 1990, the average American car had 40 microprocessors in it. And then I went, oh my God, my body is going to have 40 microprocessors implanted in 20 years. Or my granddaughter, I guess. We think about granddaughters when we think about things like that. So we then formed a group in the 802.15, and the reason that we create standards is that it helps open business opportunities, maximize research efforts. They generate public and customer trust, and build order in the marketplace and enhance safety. That's our official byline at IEEE. The purpose of 802.15.6 standard was to provide an international standard for a short range, about human body range. We picked Yao Ming as our standard. He's currently the tallest human being on Earth. So we had to go from 2 meters to 3 meters very quickly. Low power and high reliable wireless communications in close proximity to or inside a human body. Well, that phrase has given me so much grief over the last 5 years that people, you mean inside? What do you mean by proximity? Do you mean on the skin, or do you mean quarter inch from the skin? Like, a badge that's away from your skin, but it's not touching it. So is that also? Anyway, the membership of TG6, as we called it back then, was very broad and very international. Multiple companies, a lot of industries were involved. Semiconductors, of course, because they want to make a chip, and I kept telling them, "Go away till we're ready to make a chip." Besides, get used to making chips that we can swallow, which was a shock to them 5 years ago. Most semiconductors people never had to make a chip that people can swallow. They were saying, "What? You swallow a chip?" Okay. And we had a lot of applications coming out of these. And then we signed some liaisons with Medical ICT Consortium, which will have a symposium next March in 2012. In La Jolla, advertising. And eHealth 15.4, IEEE 1073, which is trying to standardize the higher level of healthcare protocols. And there used to be down on the bottom here, continua liaison, but I just checked the papers. We never signed it, and I'm going to try to nail them after the meeting today to see if we can get that also. What we accomplished so far is we formed it in January 2008, which was in Taipei. In May of 2008, we sent out call for applications. In November, we had call for proposals. And we sent out the application summary document, which is this document I mentioned with 140 application scenarios that defined basically what we were trying to standardize. We created a technical requirement document, and also we did a what I consider the premier channel model document. Over the last 20 years, I've been trying to get a real good model of what a human body is as a transmission medium. And I think in this group we finally accomplished it. We had 5 major organizations around the world measuring various human bodies, standing, lying, sleeping, walking, moving around, being in a hospital bed, sitting up in a metal chair, having transmitters in the chest and the head and the various aspects of a human body. I might mention the best paper that came was NIST's. Thank you, Cameron. He led the work. So we sent out all those channel models to people that were proposing the standard to consider it, and we were going to review the proposals based on how they worked in different scenarios in that channel. And then we received 30 proposals in July of 2009, and we began merging process. I looked much younger then. But in March of 2010, we merged to a single proposal, which was pretty amazing. And we never got into what this death in IEEE, which is 2 camps that fight each other and nothing ever happens. So we merged to a single proposal through negotiations, multiple negotiations in different meetings. First 30 went down to several groups of 5 or 6 or 7, and those groups started merging with each other, and we finally wound up to one proposal. And then we created a draft 0, and in July last year, it passed letter ballot of 76%. They had a bunch of errors, so we fixed those. In January this year, we created draft 2. That one passed. Letter ballot went up to 84% in passage, and last May, 2 months ago, we had the draft 3, and right now we're working on draft 4, fixing the last few mistakes. Hopefully this week we'll have an answer whether we're done and we can go to sponsor ballot in IEEE, or whether we need to recirculate it one more time. This is the sum total of my medical knowledge. So the doctors in the room, please don't jump all over me. When we started to do the transmission and conduction studies on human tissues, we discovered there's these 5 types or 4 types. And where we put the hub, I did not major in art. I majored in engineering. So my wife's an artist. I'm just an engineer. So we had a wrist. Where will we put the most likely location for a hub? And so wrist was put there in a necklace, like a soldier dog tag type of a thing, belt, and as positioned by IBM in 90s, Zimmerman proposal to put it in a shoe, because the heel can produce the energy with every step you walk. You can recharge the battery. never worked, but it was good. It's called IBM Proposal for Body Area Network. So the architecture is hub and node in a band. There's a hub deals with several nodes around the body. And in the process of between draft 2 and 3, we had to add a node extension. This is, well, okay. So a node can actually be a relaying node to another node. And the basic reason for that is that the human body has some deep shadows. And if you have, for example, from front to the back, even it's only, 5 inches in a thin person, you can't get there with certain frequencies because of shadowing. So we thought we would put a node here and then relay it to another node. So there's a concept of extension in this standard. We wound up with 3 PHYs. PHYs means physical layer. We call them PHY narrowband, an ultra-wideband, and HBC, and a single MAC. And in the narrowband, we have, in different bands, we have many channels in different bands. Different bands have different channels and different channel bandwidth available. Some of the data rates that will be available in the standard in terms of actual information data bits, this is after coding and error coding and all that, is listed here. In the ultra-wideband PHY, we have several channels also, and the data rates available in that one are listed here. Some of them are a little higher than narrowband, and we have 2 different types of ultra-wideband, impulse radio and FM. And then we have slightly controversial human body communication channel, where electrode is actually touching the body, and it uses 2 bands at 21 and 32 megahertz and offers data rates of 250 up to 2 megabits. The MAC features, this is the actual processing of information after it's received from a physical channel, is that we've added actually fairly extensive quality of service. First of all, we had to deal with medical and also consumer applications. So right away we had a conflict there. We decided medicals have higher priority than consumer. So if a person has a stroke while playing a video game, so they're playing their Wii, that's part of their body network, but they start having a stroke, that should have a priority on the messages to go out to the hub. We support the mixed band communications. We basically adopted everything that people in the mixed band have developed in the last few years. We supported an emergency communication. There is a concept of an emergency packet that any sensor can send if it senses something around the body that is really considered an emergency. And that one will get through and out in less than a second, no matter what else is happening in the system. And we've added very strong security, because the information that's flying around the body network is somewhat personal, especially in the medical area. And we wanted to be sure that it can't be hacked and jammed and interfered with. We've added macroscopic and microscopic power management. Those were some innovations that some of the members of 802.15.6 brought to the standards, where the nodes are virtually asleep for months, and so they can draw very low power. I mean, most people in the medical world at least want their sensors to live 5 to 10, preferably 20 years, preferably the whole life of a human being, which is coming towards 100 years. So we can't do that yet, I don't think, but next generation maybe. And then we've added coexistence and interference mitigation because in this room there may be 50 bands sitting in one room, and especially in tight places like trains or buses or airplanes, you may have few people in a square meter. So we wanted to make sure that none of those bands interfere with each other and they don't interfere with each other's work. This is some of the priority that we've had added to in the BANT. You can see the highest is the emergency or medical event report. And now some of the way that we heard people are going to use this, I won't repeat what people have said already, but some of the applications in the medical field were heart, hypertension, diabetes, Parkinson's, epilepsy, mood detection and depression, and pain management. We are starting to define now what therapy is. Therapy is sensing various conditions in the human body, processing it with therapy software, present it to the doctor or a physician with alternatives, and then allow the physician or doctor to stimulate the body with either mechanical, electrical, chemical, pharmacology, and other kinds of remedies. And we're now beginning to think what that's going to mean. Some of the early devices, I know I'm running out of time, so I won't spend much time on it. Some of them are represented in this room. The one that's intriguing me lately is the one on the bottom. No, the second one, retina implants. People are starting to put chips inside the back of your eye and transmit video out of your eye to things outside. And there's this, that's an actual picture of a French movie director that's going to be implanted with a camera in his eye. He's going to make a movie by walking around and taking pictures of his life for a year or two. That's dedication. That's dedication. Here's some of the sensors. That's part of our things that we came up. Some of the actuators. I guess the most recent one that I'm most intrigued with is the second one from the bottom. I know why I put them second one to the bottom. Is the internal body temperature measurement. Apparently some surgeries can be done much safer if you cool a person. And they want to have sensors stuck all over the human body to measure what the temperature actually is in real time while they're operating. The other thing is controlling a prosthesis on a person. And so, in summary, say thank you. Last slide. BANT standards will allow medical device intercommunications. Experiments with BANT-enabled diagnostics are proving to have high therapeutic value. There are many worthwhile applications that need to bridge the biological sensors and actuators in and or in body in the world of computers and devices. Some critical applications like firemen, warfighters require psychological monitoring. Physicians that I talk to do wish for less wires in the patient diagnostic environment, especially in the critical care. The body channel model is challenging, had a lot of contributions from many organizations, and we're currently preparing for ballot process to finish by July 18th, IEEE meeting in San Francisco. So that's